Hey everyone, this is Jayan. Today I'm diving into support vector missions. Why support vector missions? Hear me out. They are super powerful in machine learning in terms of accuracy, robustness for the wide range of applications. If you go for text classification or image classification, weather forecasting, and whatnot. But why they are so powerful? That's what we are going to explore in this series of videos, and I will break down the math behind SVM in a easy to understand way. In this video, we will start with the basics, what SVMs are and how to formulate the problem. If you are serious about becoming a top-notch data scientist or a ML scientist, watch the video till the very end. Let's dive in. I'm very excited. Guys, before going into the actual concept, let's understand the basic mathematics. If someone gave you the normal vector to a plane and a point on the plane, how you will find the equation of a plane? It's very simple, right? We will create a vector that lies in the plane and we will do dot product with the n cap. Since they are perpendicular and dot product will be 0. That's what I have done, and I am came up with this equation: ax plus by plus cz plus d equal to 0. D is a constant. Now I thought, can I able to express the equation of a plane in matrix form? Yes, we can. We can able to. How? Take W, a matrix with coefficients of the normal vector. Coefficients of the normal vector A, B, C, and the variables, nothing but the coordinates x, y, z in capital X, a matrix capital X. Let's suppose now W transpose dot x will be ax plus by plus cz, right? Now equation of a plane is nothing but W transpose dot x plus d. Why W transpose? For matrix multiplication. See, the very important part is the normal vector is perpendicular to the plane. W is a normal vector because in W we have the coefficients of normal vector, right? That means W is a vector which is perpendicular to the plane. Let's have this intuition in our mind, and we will dive into the support vector missions. And now, how to define the hyperplane? Since we have the dimension of w and x is 3, we are calling it as a plane. What if the dimension is more than 3? Simple, it is a hyperplane. That's the definition of a hyperplane. I hope you understood the definition of the hyperplane. Now let's dive into SVM. What SVM actually solves? See, we have two classes, positive class and the negative class. Positive class on the right side with plus symbol. I hope you can see the screen very clearly. And the negative class on the left side, and our aim is to classify this data. How many lines or the hyperplanes? If now we are considering two dimensions, so the line will be the classifier. If we are going to three dimension, then plane will be the classifier. For n dimension, hyperplane will classify this data. Now we will be having so many lines to classify this data, right? But I want the line which is best for the classification. How to do this? We're assuming that the data is linearly separable, which means we are able to classify data using a linear equation, because linear equation of the line is linear. Then now the question is, what is linear equation? Linear equation is nothing but an equation where each term has a degree equal to 1. Like you can see ax plus by plus cz equal to 0. Degree is 1. If the degree is more than 1, it is not a linear equation. It's as simple as that. Clearly, we define the number of hyperplanes pi 1, pi 2, pi 3 to separate the data, but we want more accurate and robust one. How to find it? We don't have to worry, guys. SVM helps us. The goal of SVM is to find a hyperplane which could separate the data accurately Or we can think it as like this also. Its goal is to find a hyperplane that gives the maximum separation between the classes. See, very easy to understand, right? Find a hyperplane that gives the maximum separation between the class. That's what we want. Maximum separation I want. How to make sure the line that we had, that we got, or the line that SVM founds has the maximum separation between the two classes. For this reason, the alternate term to call SVM is maximum margin classifier. We also sometimes use maximum margin classifier to refer SVM. See, you can see the screen, right? Separating a hyperplane. Now, what is margin? Margin is nothing but the distance from the hyperplane and the plane which has the support vectors. Which has the support vectors. I am considering the equation of a plane as W transpose dot x plus d equal to 0. Before we saw, right, the equation of the plane. That is only I took that equation here. Now let's understand. Let's formulate this. Let's formulate how we get the maximum. Now what we want to maximize this distance, the distance between the hyperplanes. See, we have a hyperplane pi. We have pi minus and pi plus. We want to maximize the distance between pi minus and pi plus. And no other vector, any vector will not be inside this pi plus or the pi minus. That is why we are calling the SVM, the linearly separable SVM, as hard margin SVM. Why? It is very strict regarding the data points. The data point should not be inside pi minus or inside the pi plus. See, any point should not be inside this. It is very strict. That's why we are calling it as hard margin. And let's formulate how to make this distance more. It's a distance between the two planes, pi minus and pi plus. How to maximize this distance? Let's formulate guys. It's one approach, the geometric approach we are using. The equation of a plane pi, we saw it before. W transpose dot x plus d equal to 0, and you can see W and x are this. As we are looking to maximize the margin, see, maximizing margin is nothing but maximizing the perpendicular distance, right? You can see clearly margin between positive and negative data points. We would like this positive data points to satisfy the following constraint. See, following constraint pi plus. See, we are defining another plane, another hyperplane as W transpose dot xi plus, because all the positive points should satisfy this condition, should be above from this line, above from this plane. You can consider any of them above by introducing some margin, introducing some functional margin, the plus one. See how we are going to make sure that every point is after this pi plus, because by introducing some margin, right? If a point, if you take a point and substitute in this line and its value is greater than 1, oh, we will understand, okay, that point is above this line. Means we created some matrix such a way that if we substitute some point on this, we will get some point on this equation pi plus. We will understand, okay, this point lies above that plane. I hope you understood. Similarly, for negative points, we created one matrix, another hyperplane pi minus. After this plane, all the points should lie after this plane, below this plane, below this hyperplane. See, W transpose dot xi minus. See, all the negative points should be less than this. Should be after substituting that negative point here, we should get the value that should be less than minus one. Should be less than minus one. Then we will, okay. That point definitely will be in this class. You can see my cursor. You can see my cursor, right? Now we can use a neat trick. to write a uniform equation from both. Can we have a one equation for both these conditions from these two equations? Can we make one equation from these two? Yes, we can. How we know this? We know their label, right? We know their label. Positive class has label plus 1, negative class has label minus 1. Now let's see. We can, if you take any data point xi, it will satisfy this condition. See, I multiply. Let's suppose yi is plus 1. Plus 1 into w transpose dot xi plus d greater than or equal to plus 1 means that point is lying above it. That point is lying above this equation, above this plane, right? Pi plus. Yes, that's what. If you keep minus 1, if you keep yi equal to minus 1, then the inequality symbol will be reversed and we will get the right side as minus 1, and we will come up with this plane. If you keep plus 1, we will come up with this. If you keep minus 1, we will come up with this. Means this equation provides the information of these two equations, these two hyperplanes, right? Okay, now we formulated our condition. Now we aim to maximize the distance between the pi plus and pi minus, which means the maximizing the margin. Now let's understand. Now let's understand how to get that perpendicular distance. How to get the perpendicular distance. I'm taking a point on pi minus, which is xi minus, because it belongs to negative class, and another point on pi plus, which is xj plus pi plus. Now, using triangular inequality, equal you can triangular law, we can say that xj, now xi plus z, this z is equal to xj, right? That's what I have written. This z is equals to xj minus xi. Means we got the vector, and we want the perpendicular distance. We want the perpendicular distance, the perpendicular distance between the pi minus and pi plus. Okay. Since we can move the vectors freely, what we will do is we will do the projection of this z on this w vector. And you might have this question: why w vector is perpendicular to pi minus or pi plus? Guys, that is why I explained the equation of the plane at the start. When we formulated the equation, w vector is perpendicular to the plane, right? Because it is a w contains the coefficients of normal vector. That is the reason w vector is perpendicular to these planes. Now if we able to find the projection of this z on this w, we will get the perpendicular distance. I have done that itself. Since we can move the vectors freely, we want the projection of z on this w. Clearly, the projection of z on w gives the distance between pi minus and pi plus. Now, f of w will be, what is this f of w? This is nothing but the projection. Projection of this vector. What is the projection of a on b? A bar dot b bar by modulus of b bar, right? In similar way, projection of z on w, z dot w by norm of w. What is norm? Norm is nothing but, if you don't know the linear algebra, norm is like the modulus of a vector. You can think of like that. See, now I just taken this w inside, and xj dot w minus xi minus w xi dot w by norm of it, and we know that guys, xi lies on pi minus. See, xi lies on pi minus means it satisfies the equation of pi minus, right? I have done that itself. See, xi dot w plus d equal to minus 1, and xi dot w equal to minus 1 minus d, right? We got this xi dot w. Similarly, xj lies on pi plus, and xj dot w plus d equal to plus 1, and we came up with this xj, and substituting this 1 and 2 in 1. Let's see what will happen. And we got this. We got f of w is equals to 2 by norm of w. 2 by norm of w. Now what is our aim? Our aim, the what SVM going to do is it will maximize this f of w. This f of w. What is the meaning of this? See, what is our goal? Maximizing f of w for what values of w and d we will able to maximize this is the meaning of this function here. For what values of w and d we will able to maximize this f of w subjected to a constraint. We have a constraint, guys. What is that constraint? That constraint is this: negative point should be below the pi minus, positive point should be below the above the pi plus. That is why it is very hard, it is very strict, and we are calling it as hard SVM, hard margin SVM. I hope you understood the problem formulation. We are going to maximize this f of w subjected to this constraint. Now how we are going to do this? Who will help us? I, I think you might know the Lagrangian. The Lagrangian will help us to maximize this function. To maximize in the next video, part 2, I will going to explore the Lagrangian multiplier method to maximize this f of w. That's it for this video. Guys, if you have any doubts, drop in the comment section. I will share the notes. Link will be in the description box. And if you got any value from this video and understood something, subscribe the channel, like, share, and thanks for watching. See you in the part 2. Don't miss it out.